just kind of get, and you'll get an intuitive feel for these rules, and so don't worry about memorizing them verbatim. What we're looking for here is just an understanding. So let's say I'm going to use c as a constant, and I'm going to have two limits of two different functions, f at x and g at x, approaching the same value a, and all I'm going to do is I'm going to stipulate that those limits exist. Okay, so we're going to look at what we can do with various combinations of these things. Okay, so the first one, it says if I'm going to add the two functions together and find the limit as x goes to a, I can do that by calculating the limits separately and then adding the result. Okay, so think about that. I take a function, I add it to another function, and then I find the limit of that going to a. I could do that, or I can do the opposite of that. I can calculate the limits individually and then add them. So generally, what you're doing is you're taking the left-hand side of that equation and you're calculating a limit by using the rule on the right side, but it also goes backwards. If you want to combine limits, you can do that. Yes?
Is it supposed to say x to b there? Since we were only going to a.
Oh yeah, it should be x to a.
Thank you. Yeah, I have my notes to be wrong.
All right, and of course, subtraction is just the...
Which one's x to a? The second.
Let me, I'll make the correction here. Okay, this should say A.
That's some sort of weird transformation.
How's that?
There, and this
Okay. Yeah, and so this also works for subtraction. If you look in your book, they'll treat it as two separate rules. That if you take the difference, f at x minus g at x, you can calculate the limit separately and then take the difference as well. So, you know, addition and subtraction are kind of opposite sides of the same coin, if you want to look at it that way.
You have
Yes?
to pick and choose which one you subtract first,
No.
or just the first is given.
No, it's just, this is just a relationship between two functions.
Okay.
Is there a word for the A? Like, does it have its own name? Is there, it's like a limit, it's kind of its own limit too, like, but is there a word for
Well,
it?
A is what we're trying, as x goes to A. It's generally going to be a number like 0 or, you know, 5 or, you know, sometimes infinity or whatever, but that's just some value, I guess, is a way to look at A. Okay, so as x goes to some value, and since, you know, we have the same value, it's the limit evaluated at both places.
So in this case, a is just what's standing in for this value that x is going to. But will there ever be a time when we have the limit answer to the limit, but when we have to find out where x is going?
No, it's definitely this direction where you're going to take x to a certain value and then find what your function is going to. Yes.
Okay, thank you.
Okay, so then the next rule is that if I take a constant times a function, I can factor out the constant and find the limit to the function first. So if I know the limit of a function, I know the limit of every multiple of that function. I just do the multiplication. So this is just to remember that, you know, if you know that, let's say, the limit of x squared, then you know what the limit of 3x squared is as well. Now, it also works for products. So if we have two functions that we're multiplying, we can find the limits of those functions separately and then multiply the limits together. And then finally, if we take the ratio of the functions, we can find the limits and then do the division. The stipulation here, though, is that the limit as x goes to a for g at x can't be 0, because then, of course, we're doing division by 0. So it is possible that f at x divided by g at x has a limit, and you can't calculate it by calculating the limits separately when g at x equals 0, because it's quite well possible that there is some other function that will give you, or some other technique that will give you f divided by g it'll give you a real live limit. It's just that the limit of g at x can't be 0 if we're using this particular relationship.
Is the first limit the x to a?
Yeah.
So
Oops.
g cannot equal 0.
Yeah, this is a down here. Okay?
So those are the functions themselves going into the multiplication and division.
Mm-hmm.
We're just excluding the limit and shoving it outside, okay.
Okay. Now, I'll have these charts posted, so if you're not writing quite as fast as I'm talking, that's okay. You can pick this up off of Moodle. Okay, so we have a few more limits. Now remember we had the rule where you can take the product of f and g and find the limit. You can find the limits separately and then multiply them together. That will extend into exponents. So if you have some function that you're taking to the nth power and finding the limit there, you can first find the limit of the function and then take it to the x power. And we'll have some examples pretty soon. So just focus on what this is saying, that if you have, let's say, you're trying to find the limit of, let's say, as x goes to some value of x squared, we can find the limit as what x goes to and then square it. So we can do kind of the inner limit first, if you want to look at it that way. Now, remember, c is a constant, so the limit as x goes to a of a constant is just that constant, right? There's nothing that x is going to do that's going to change that constant. So if we ever have, to take the limit of a number, it's just that number.
So the limit of 3 is 3.
Correct. Now, if we have just a variable, just x, the limit as x goes to a is a. Okay, that might seem almost trivial, but it's one of the most important limits that we have. So if x is going to go to a, the limit is going to be a. All right, not real hard to remember. And then we also have, because of the first and that first line and that third line contribute to making that limit of as x goes to a of x to the n equals a to the n. And then the exponentiation rule also translates into roots, because remember, taking the root is taking using an exponent as a rational number, not just as an integer. So, x to the 1/3 works in the first rule, and so if we make that in radical form, we get the second two, where we can take the roots before and after we find the limits.
So root, same works with x equals a no matter what, even if it's rooted or squared or something. Okay.
That's correct. Okay, so then what we have now is that we can find the limit of any polynomial function and rational function. Yes.
And it's okay if we don't fully understand this, right?
Well,
Or,
you should
the-
fully understand it,
the-
but once we do some exercises, you'll see
That's what I meant.
you'll see the utility of these. It's not. I'm not ever going to ask you to quote these, but you're going to use them, and you're going to get to be to the point where it's automatic, almost like you may not be able to identify the associative and distributive property of arithmetic, but you certainly know how to use them. Okay? So when I go through the examples, all of a sudden you'll see, this makes sense, and this is actually a little easier than it looks right now. Okay, so here's time for an example. I gave you a whole bunch of rules. I'm going to do this one in excruciating detail. And that means that when you're doing this particular limit, You don't have to do every step, because once you see what this is about, it's going to just pop for you. Okay, so let's say I want to find the limit as x goes to 2 of x squared plus 2x plus 1. Okay, so I don't have any rule that gives me a polynomial per se, but I have all the components that make up a polynomial. I have the rules that apply to them. So the first thing I can do, since a polynomial is sum of terms, is I can break these 3 terms up into 3 limits. So I can take the limit as x goes to 2 of x squared, the limit as x goes to 2 of 2x, plus the limit of 1 as x goes to 2. Okay, so that's the first thing. I can say that the sum of those things, the limit of that, is the sum of the individual limits. Okay, and then I look at the first, I can simplify to some degree all of these, where if I find the limit of x squared, that's the same thing as finding the limit of x and then squaring it. Okay, we had a rule to do that. And then I have a constant 2 times x, and so I can say that it's going to be 2 times the limit of x. And then the limit of a constant like 1 as x goes to 2 is just 1. All right, and so since I know what the limit of x is as x goes to 2, that's going to be 2. I can take 2 squared plus 2 times 2 plus 1, and I get 9. All right, so that's a lot of writing and a lot of thinking. Now, remember I said this is a polynomial and we have all the tools for this thing. What we can do is just make the substitution. Okay, so this is way simpler. So if we know it's a polynomial or a rational function, and this is the important point here, and A is in the domain of f, then we just plug it in. So any polynomial has a domain of all real numbers, right? There's rational functions we have to worry about division by 0. But a polynomial is just a sum of x to various powers with coefficients in front of it. So any polynomial that we want to find any limit to, where a is a real number, we're not talking about infinity now, we're talking about just any kind of real number, we just plug it right in. And so there's one caveat here, that you have to pay attention to the conditions where this works, that it works for rational and it works for polynomial functions, and with rational functions, A has to be in the domain of f. So as x goes to 0 of 1 over x, 0 is not in the domain of 1 over x, and so you can't calculate it by plugging it in. And if you did, you wouldn't get a number, right? 1 over 0 is not a number. So any rational number that evaluates to a particular point, that a is part of the domain, you can just plug it in.
So you can just move things around so that the limit is always x, which turns the limit into a, which is why I don't need a calculator anymore, right?
Well, no, that's not it. X is in the definition of your function, and so you evaluate the function at a.
Yeah.
Okay, so now here's another rule, and this one's a helpful rule, and it's going to help us out with that case where we have 0 over 0 in a lot of things. This will look kind of odd. If f at x equals g at x when x doesn't equal a, then the limit as x goes to a of f at x equals the limit as x goes to a of g at x. Okay, so the unusual part of this is when x doesn't equal a. So if we have a function that in all the areas that we're interested in, f at x and g at x are the same, then we can say that the limits of those two functions will go to the same number. Now this is going to help us out where the cases where we have 0 over 0. So let me take this example here. So I want to take this rational function, x minus 1 over x squared minus 1, and I want to go, as x goes to 1, what is f at x? Now, 1 isn't part of the domain of this function because 1 minus 1 divided by 1 minus 1 is 0 over 0. So when x is 1, we're not in the domain. So our rule of just plugging it in doesn't work here. So what I'm going to do is I'm going to take this function and I'm going to factor it, and then I'm going to simplify it, and I'm going to call that g at x. Okay, so I'm going to factor out that x squared to be x minus 1 times x plus 1, and so the x minus 1's cancel, and I get 1 over x plus 1, and that's g at x, okay? So for every value except when x equals 1, f at x equals g at x, right? Because these are equivalent expressions with the exception of where the domain, where you have the domain exclusion in f. And so now what we can do is we can just take the limit of 1 over x plus 1 and say that's 1/2, and that tells us then that the limit of f at x as x goes to 1 is 1/2. Oops, sorry, that's too fast. So think about this. What this is saying is that think about what we know about rational functions, and this is part of why we went through all those exercises earlier about, you know, what do the graphs look like. When we have something like this here, if we were to graph that, what we would get is the graph of 1 over x plus 1 with a hole at x equals 1, right? The holes are where the factors cancel. So that basically says that f at x doesn't evaluate at 1. But once we simplify it to this, and if I call g at x this, we don't have a hole anymore. And so the two functions coincide except for that hole. And so what this helpful rule says is that if your function is the same everywhere except where you're trying to find the limit, then that limit is the same for both of the functions. And so this is the notion really of a limit. It isn't just a matter of plugging in an a to get whatever f at a is. It is as x goes to a, but x does not equal a. It's how close do you get? You can get as close as you want, but x is never a. It's as x gets closer to a. And so the limit is in polynomial functions f at a, but that doesn't ever mean that x is equal to a. Okay, just kind of a subtle point, but this is, all this stuff kind of hangs together because we're thinking about limits as a notion of as x approaches a, not as x becomes a. All right? Okay, so let's have a couple examples here. We have, this thing should look like the difference quotient to you now. Okay, this f at 2 plus h minus f at 2 over h. Before I've used delta x instead of h, okay? So what I want to do now is find the limit as x goes to 0 of these functions. And notice this function is just x squared where x equals 2. So this is what you did with that take-home assignment and what you did in tutorial yesterday, is find the derivative of x squared where where x equals 2, right? You get that from this limit that you saw the very first day of class. And so if we were just to plug it in, you'd get 0 over 0. But what you do is you expand it and you simplify it. So if I just took my function, my x squared, and I put in 2 plus h for the 2 plus f at 2 plus h, and I have 2 squared for my f at 2, and then h remains. And now I'm going to expand it and then simplify it. You see where I've had, I get a 4 and then I get a minus 4 at the end, and all the terms, the remaining terms have an h in it. If I then cancel out the h's, divide, factor out the h and cancel the h, I get 4 plus h. So here's an equivalent expression for this thing. And so with all the rules that I've had before, now I know that the limit of 4 plus h as h goes to 0 is just 4, right? Because the limit as the limit of h as h goes to 0 is just 0. Now we'll talk a little bit more about finding derivatives and how you set them up and how you get this equation working for you. But here the illustration is just, these are the kinds of things that you're going to see. And so the first strategy of calculating this limit is simplifying this expression to eliminate the fact that you're going to get a 0 over 0. And we get this equivalent function, which is just 4 plus h. And then we can calculate the value, the limit of that. Yes?
Where did f of x equals x squared come from? Where did I get it?
This is just to kind of illustrate that this particular thing is the difference quotient for f at x equals x squared, where x equals 2. Okay? And setting this thing up, we'll spend a lot more time with it. But my point here is that this is what you did graphically yesterday and also numerically, right, by calculating your table of values. Here we did it algebraically, and it was actually quite a bit faster. Now sometimes we get really funny looking expressions, like this one on the board, okay? This one is difficult to calculate because, of course, when you put in x equals 0, we get 0 over 0, so we can't use that rule because 0 is not part of the domain of this function. Same thing with the one up there. We get 1 plus 0 is 1, the square root of 1 is 1, 1 minus 1 is 0, as h goes to 0, you get 0 over 0 again. So we need to find some way to simplify this. Now with radicals, it may not be really, really obvious, but one of the things that was emphasized to you in wherever you took algebra is that you can rationalize numerators and denominators by multiplying by the conjugate. And here, even though we have the radical in the numerator, what we want to do is we want to rationalize that because when we multiply it by its conjugate, we get something that's really kind of nice. Look at that square root of 1 plus h plus 1. As h goes to 0, that's going to actually be a non-zero number. So remember how conjugates work when you take the square root of 1 plus h minus 1 times the square root of h plus 1. You get, these two things multiplied by each other. This first term is squared, and it's subtracted from the second term, which is also squared. So if I expand that, what I get is just the square of the of that radical term here, the square of this minus the square of that 1, and so we get 1 plus h minus 1, and then in the denominator we have the h times that conjugate factor that we put in there. All right, so if I then simplify this a little bit more, I get subtract the 1 from the 1, and I get h over h times square root of 1 plus h plus 1. And then this, of course, simplifies into 1 over that radical. Now as h goes to 0, notice that expression that I've come up with here is now a 0 is in the domain of that, right? If we were just simplifying it outside of this thing, we would have to make the domain exclusion h does not equal 0. But here's a function that everywhere else except 0, it's the same thing as what we started with. We can directly substitute the 0 in there and we get 1/2. So we know that the limit then of the original function is 1/2. Okay, so I'm going to pause here for a minute. Yes,
equation?
and it will come up. It will come up pretty regularly that you have something that goes 0 over 0, and unlike the previous example where we could just expand it, there's no expanding this.
Okay.
So one of the ways that you can deal with this then is multiply by the conjugate. Okay, so remember we went back to this definition of the limit, that the limit of a function exists only if the limit from the positive direction and from the negative direction are the same value. Okay, so the right-hand limit and the left-hand limit have to be the same thing in order for that one limit to exist. So now let's look at the function, the absolute value of x. And so how do we do this? Now the absolute value of x is neither a polynomial nor a rational function, right? It's a special function. And if we want to get to the definition, the absolute value of x is a piecewise function. Depending on whether x is greater than or less than 0, we have two different definitions. And so in order to do this rigorously, we calculate from the negative and from the positive side. So if we're going from the negative side, the left-hand function, or the left-hand limit, we have the absolute value of x, you know, is always going to be negative. And so that's the same thing as writing the limit as x goes to 0 of negative x, because the negative x will make that x positive then, or make the value of the whole expression positive. That's what the absolute value does. And so we can evaluate this one directly as x goes to 0, negative x goes to 0. Now when we're coming from the positive direction, we're taking the right-hand limit, so x is always positive, the absolute value leaves x unchanged, and so we just have the limit as x goes to 0 of x equals 0. And so since we've taken two functions, or the two pieces of this function, and we've made the left and the right-hand limit, we calculated those and they come to the same thing, then we can confidently say that the limit as x goes to 0 of the absolute value of x equals 0. So when you're applying the rules that we went over, you have to be really careful about the definitions of these things, that we're not just applying the substitution willy-nilly, that we have a good reason for doing it, and if we can't do it, then what we need to do is find other means. And in this particular one, since the absolute value of x wasn't a polynomial or a rational function, we do the left and the right-hand limit because they do evaluate to the same thing, and we get this limit in a little bit more rigorous fashion than just a guess. Okay?
Wait, what happened? What was the plus and minus for?
Where?
When you're solving the limit.
Here or down here?
Down there.
Well, the absolute, if x is negative, the absolute value of x is the positive. So what the absolute value does is it actually evaluates the negative number. So if x is negative 2, negative 2 is 2. Okay, and so that's where it's just part of the definition of the absolute value of x in the piecewise function.
Oh, so we're trying to solve x equals 0.
We're trying to find the limit as x goes to 0. Okay, now I'm going to introduce a new function to you, and this is called the largest this particular function finds the largest integer that is less than or equal to x.
Is that a bracket?
That's a bracket with a double line on it, okay?
Okay.
All right, so let me give you a couple examples just to clarify what I mean by that definition. If I take this function and put a 4.8 in there, the largest integer that's less than or equal to 4.8 is going to be 4. Okay? If I just take this function of 4 you get 4. And if I do -3, I get -3, because that's the largest integer that, that is less than or equal to -3. Now this is the surprising one, or at least the one that takes some getting used to. -3.2, the largest integer that is less than or equal to -3.2 is -4. It's not -3, because -3 is greater than -3.2. And the definition is strictly the largest integer that's less than or equal to x. And so this function is useful when you have a real number and you want to convert, or you want to make it into an integer or something like that. It comes up in a lot of different things, like when you're, let's say, paying for parking or so, and you're going to pay for any piece of an hour that you park and things like that. There's functions like this that will make your 20 minutes into a 1-hour charge or things like that. You can use this function for defining those kinds of things. Okay, so let's look at a graph of this, what it looks like. And we have this thing as a step. So if we look at a particular value in here, we see that if x equals 3, then that function equals 3. If it equals 3.5, it still equals 3 until we get to 4. And then if it actually equals 4, then the function equals 4. If it's very, very close to 4, it still equals 3. So it makes this kind of stair step. So now what I want to do is let's calculate the limit of this thing as x goes to 2. So this doesn't correspond to any particular rule that we have. So I'm going to take the left and right hand limits because those I can evaluate. So if I'm coming from the negative side up to 2, okay, I'm on this line, so I'm coming from the negative side and I'm going up to 2. That means that function is going to equal 1, so the limit of that function is 1. And then if I'm coming from the positive side, I'm actually on this step, and so I'm coming down to 2, and so my limit as I approach 2 is 2. And since we have the left hand and the right hand limit as having a different value, the limit as x goes to 2 of this doesn't exist. Okay?
Why doesn't it exist?
Because the left and the right hand limits aren't equal. They have to be equal for that limit to exist.
Why is one equal 1 and 1 equal 2? That's why I'm confused about.
Well, that's because of the definition of the function. As you go from the left-hand side, as you approach 2, your function equals 1. And as you approach 2 from the right-hand side, the function equals 2. And so the limit of this step is 1, the limit of that step is 2. So if we try and evaluate the limit at 2, we approach it from both the left and the right and find that we have two different values. Okay, so now I'm going to introduce two theorems, and I want to say a couple words about theorems before I actually introduce these theorems. Mathematicians use theorems as a way to build up a body of mathematical properties that you don't have to go back to basic principles to solve each and every time. So a theorem is something that has been proven to work for whatever case the definition of that theorem encompasses. So a lot of the rules that I showed you are actually theorems that you say, if this exists, then this is true. And so it's a way that you can really shortcut a lot of problem solving by applying certain theorems, that you don't have to go back and from basic principles apply everything else. Like, we said now we can find the value of a limit of a polynomial simply by substituting in the value, that a value, that we could state as a theorem. If f at x equals a polynomial, then the limit, as x approaches a of f at x equals f at a. So I'm going to break this theorem up into two parts. The first part is the if part. Okay, so this is the thing that establishes the conditions that this theorem applies to. So I'm going to say if we have two functions and one is less than or equal to another function when x is near a, except possibly a. So that I'm saying that a doesn't have to be in the domain of either of those functions, or if it's in the domain, that it may even be a different value. But what I'm saying is that when we're near a, the two share this relationship where f at x is always smaller than g at x. And then I'm going to say that as we approach a, both of those limits for f at x and g at x exist. Okay, so there's the definition. If I have that condition, then this part is true. Then the limit as x approaches a of f at x is going to be less than or equal to the limit as x approaches a of g at x. So if you know that f at x is always less than something, then the limit is going to be less than the function that you're comparing it to. Now this in itself isn't as useful as the next theorem, but the next theorem depends on this one to prove it. So it's something called the squeeze theorem. Now you'll see this theorem by different names. Our book calls it the squeeze theorem, and I think that's probably the most common name for it. It's also sometimes called the sandwich theorem. Okay? And what this says is that if I have three functions, where g at x is always between f at x and h at x, except possibly at a, and we have the limit of f at x as x approaches a equals the limit as h at x approaches a. If they equal the same thing, then the function that's in between them, okay, so there's the conditions, then the function that's in between them is going to have that limit. Now let me draw on the board what this is really saying. Okay, let's say I have a nice orderly function that looks something like this, and I'm going to call this f at x. And then I'm going to have another function that will look like this, that I'm going to call h at x. And let's say I can calculate the limits anywhere of those two. Now let's say I have this wild function that I don't necessarily have a nice uniform expression, okay, but if it dances all around, but it's never outside of the bounds of h and f at x, we can say, since it's the limit of h at x and f at x as x approaches 0, let's say we can both calculate those and those turn out to be 0, or some other value, it doesn't have to be 0, then we know that the limit of, this is g at x, then we know the limit as x approaches 0 of g at x equals 0 as well. So this is going to be used as a tool that when we can't find a limit of a function explicitly, that we can perhaps define a function that is always greater than or equal to it, and a function that's always less than or equal to it. And if those two limits squeeze down, and there's where it gets its name, or it squeezes down to the same value, then the function that's between them also has that same limit. If you think about it, it might be rather intuitive, but it's something that needs to be proven mathematically, and we're not going to go through the proof of that. But we can just take it on faith that this is a mathematical theorem, and we can always apply this. So where this comes into play, and we're not talking about the sine and cosine functions, in Math 13, but the sine function is always between -1 and 1, and so if we have this thing oscillating because of the sine function, we can just take the sine's limit of 1 and -1 and put that above and below and see where that function goes. So with rational functions, it's hard to come up with an example of this, but we're going to talk about continuity next. That's going to be Monday's topic. On Wednesday, we're going to talk about limits as x approaches infinity. And so when we get to that point, then the squeeze theorem is going to be very, very useful for us. And just let's say you have I'll give you the example orally, that if I have some function that I know as x goes to infinity goes to 0, and the function that I'm trying to figure out the limit of, if that thing is always positive, then between 0 and that upper limit squeeze down to 0, so the one that's in between them also goes down to 0 as well. And so that'll be a useful thing that we can simplify certain functions and calculate their limits a little bit more readily. Okay, and I'll give the example then. Your book introduces the squeeze theorem right now because they also are using functions like sine and cosine. We're not going to do those, but since it was introduced now, I thought I'd introduce it now because it's part of the kind of the overall rules of limits. Okay.